Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be talking about the Stokes Law Drag. So this is a drag force that fluids, especially liquids, tend to apply when they're undergoing laminar flow about an object. It can be due to the liquid flowing around the object. So you could have a stationary object and a moving fluid, like in a river, for example, flowing around a boulder. You can also have the object falling through the fluid, like a rock dropped on a lake. And of course, it's also possible to have both things. For example, if you drop a rock into a river, the rock is falling downward and the river is moving more or less horizontally, let's say. And so you'd have both things move. The important thing is that the object is moving relative to the water, or the water is moving relative to the object, so that there is some relative velocity between the two. We can begin by recalling a few facts, a few concepts, and so on. For starters, we have the drag force for air resistance. So this is air resistance drag was velocity dependent. So the force of the air resistance drag actually is proportional to the cross-section area of the object and the speed squared. I'm not writing the whole equation out because it doesn't especially concern us. The main point is that the drag is proportional to the speed squared, and it's also proportional to somehow the area of the object. This will be in contrast with today's law. So this is in contrast to today's law, or today's drag force. Second thing that we might recall is that viscosity is a sort of friction between layers in a fluid. So viscosity, we could say, is friction between fluid layers. Third thing to recall is that we like to work in the laminar regime. So laminar flow basically means that we have a streamlined fluid flow, and that includes around an object. And so that essentially means that each layer of the fluid kind of follows out its own sort of like path around the object. And this laminar flow is one of the conditions actually for Stokes Law drag to occur. So if you do not have laminar flow, then you will likely not have a Stokes Law drag. For example, if the flow is, instead of being laminar, if it's turbulent, then the drag changes quite dramatically. And in fact, this right here tends to have some turbulence built in. The conditions with this air resistance drag is typically fast-moving object in a low-density fluid, meaning like a gas. So like a solid, fast-moving object moving through the air would fit this. Stokes Law drag basically requires that we have a relatively slow fluid, or relatively slow motion of the fluid relative to the object. That is in contrast with the air resistance, where V can be and often is quite large. The other thing is that with Stokes' law, strictly speaking, we assume a spherical object, but there is a generalization for non-spherical object. So Stokes Law proper assumes a spherical object, but there is a sort of modification to it. So we could say can be modified for non-spherical objects. For example, if you have a boulder that's not actually a sphere shaped, then you maybe would modify the Stokes Law to account for how much drag the fluid is, the water is putting on the boulder. Stokes Law, the force is given by 6 times pi times eta times r times v. So what are all these terms? Well, this one right here is your viscosity term. So this is the coefficient of viscosity. It should be in poise, that is Pascal seconds. And you can generally look up the coefficient of viscosity for different fluids. It's temperature dependent and so on. This is the radius of the object. And then this term right here is relative velocity of object with respect to fluid. And so of course that could mean that the object is moving as viewed in our frame. It could also mean that the fluid is moving within our frame, or it could be that both. But we need to be in the reference frame, let's say, of the fluid, and then figure out what the velocity of the object is. Okay, so this is Stokes Law drag in general. If you want to write it with a vector form, then you put a minus sign on it. The drag is opposite the direction of this relative velocity. And then the generalized or modified version basically just has, or we should maybe call this the generalized version. So generalized Stokes Law basically just has the form F. We could say like generalized Stokes or something like that is negative B times V. So this B term right here in this equation is like the 6 pi eta r term in this equation. So basically what we're saying here is that the drag coefficient happens to be 6 pi eta r when we're in a Stokes Law regime of a spherical object. Generally speaking, this term includes the viscosity in it somehow, and it includes some sort of a length scale term. So if you do not have a sphere, then maybe the length scale term is like the cross-section length for a square object or something like that with a square-shaped cross-section. Alright, so for an example, let's say that we have a sphere-shaped boulder that's in the water. You got water flowing past the boulder, and basically it's going to have to flow around it somehow. And the water speed as it moves past is given by 0.5 meters per second. So it's not especially fast-moving water. The water is at 20 degrees C. What this tells us is that the coefficient of viscosity is 1.002 millipascal dot second. You can look that up from a table. This right here gives us the radius. This right here is the flow speed. So we expect for this Stokes Law drag force to be 6 times pi times eta times r times v. And so that's 6 times pi times eta, which is 1.002 times 10 to the negative 3 Pascal seconds, times 0.5 meter per second times 1.0 meter. So we can plug these things into our calculator. 3 pi is a little bit less than 10. So to a very good approximation, this is going to be 10 to the minus 2 newtons worth of drag that we're getting here. To a slightly better approximation, we're looking at a Stokes Law drag of about 9.4 times 10 to the negative 3 newtons worth of drag force from this water on this. There is, of course, a hidden assumption here, which is that water flowing at this flow speed past this boulder would actually be laminar. Is that assumption actually valid? And the answer to that question is actually no. It's not necessarily valid that this is totally laminar flow. In another video we will learn how to calculate a quantity called Reynolds number, which is an indicator of whether the flow will be laminar or not. For what it's worth, the Reynolds number for this particular problem is just a little under 500,000, which means that you have quite a bit of turbulence, though it is not totally turbulent all surrounding your boulder. So again, this is assuming, perhaps incorrectly, that what we have is laminar flow, which we do not in fact have in this particular case. Alright, so what about the possibility of an object falling through a fluid? As we did with the other drag force, the air resistance drag force, we might talk about the possibility of terminal speed. So if I have a fluid here and I have an object which is falling through the fluid at some speed v, then I know that my total forces on it will be a buoyant force as well as a generalized Stokes force. And then in the opposite direction, I have m times g. Well, this one right here basically is basically like density of the fluid times g times volume of object. This right here is volume of object times density of object times g. That's for the buoyant force, and then for the drag force, I have some b times the velocity v. It is an upward drag since the object is falling downward. So my sum of forces in this case is going to look like rho of fluid times volume of object times g minus volume of object density of object times g plus b times v. And that should equal the object's mass times its acceleration. Okay, well, we can rearrange this equation obviously, but we can also note that for some value of v, since the speed v can increase, for some value of v, this equation can be 0. We are, of course, assuming that the object is more dense in this diagram than the fluid, but if the opposite is the case, then essentially the object will be moving upward and the drag force will be downward. So it will change a few signs here. The end result in any case is that you have a terminal speed. So v equals v terminal if sum of forces equals 0. And so that means that the terminal speed is equal to the volume of the object times g times the difference in density between the object and the fluid, all divided by the drag coefficient b. Okay, so that is terminal speed for these cases of a Stokes Law drag. Some objects actually will hit the terminal speed in the Stokes Law regime, others will enter the turbulent regime first. That's all for today. Thanks for watching.